Welcome to the latest episode of TigerBytes, where we spotlight and celebrate best practices in online learning from all across campus, hoping to share some insights and maybe inspire some folks to get involved in online learning. Today we're with Stuart Loch, who's a professor in Auburn's physics department. He studies theoretical atomic physics, which hopefully you can explain what that is. He was selected by Auburn students to give the 2013 final lecture, which is a huge, huge honor.
It was a lot of fun to do it that day.
What was the theme of your final lecture?
Oh, that's a good question. So actually, I, at that time, rarely liked to give advice to anyone. So I found it kind of hard to know what to say. So in the end, I decided I would actually give advice. And so some of the advice was, when you're at Auburn, there'll be people from all over the country, all over the world. You should take advantage of all these different cultures and kind of get to know and broaden your horizons, and a little bit about the thought process of what you learn in a college education, separate from just the physics and class material, but the kind of way of thinking and way of solving problems. So I don't remember all the stuff that I said, but I had to work quite hard to make myself give advice. I tend to just let people follow their own path for things.
Gotcha. So you also served as an alumni professor from 2019 to 2024. Another big kudo for your
thank you
accomplishments. How did you end up at Auburn? What was that journey like?
That's a good question too. So all my education was back in Scotland, in Glasgow, one of the bigger cities. And so my undergraduate degree was there, my graduate school was there. And so my first job after my PhD was as a researcher here at Auburn. And I had one of the researchers in the group I was with back in Scotland. He used to work here in the 1980s, I think it was, in the physics department. So he had kept contact with people here. He kept visiting them. So he let me know about the research job that was here. So I came here as a postdoctoral researcher first, and then in 2006 applied for a faculty position here that was advertised, and then became faculty just after that.
So what was the biggest adjustment in terms of that move? Going from a big city in Europe to a small town in America.
Yeah, it was great. In fact, so I arrived here January 2002. In Scotland, in January is dark and cold, and I love growing up and living in Scotland. But I arrived mid-afternoon at Atlanta Airport, looked up, and there was no clouds in the sky, and I realised I had never seen no clouds in the sky before. That Scotland there's always clouds somewhere, and I thought, I think I'm going to like it here. This is pretty good. And then I really liked the small college town atmosphere, and I loved the research I was doing, and then really loved teaching once I started it. And so, it was a nice place to move to.
Super.
And it really is true that the kind of southern hospitality part of things, that people made me feel very welcome this year.
So you've done a bunch of projects with Auburn Online. Before I ask about that, I want to ask, what was it that made you interested in physics and teaching physics?
So it was a high school physics teacher. And so in my high school, I wanted to do an advanced physics course, and they didn't have a class in that. So in Scotland, they have a rule, or at least had it at the time, that if they can't offer a class, they have to find a neighbouring high school that offers it. So they got me taxes to go to this other school, and they had a teacher who taught some more advanced physics. And up to that point, I wanted to do mathematics. I liked math a lot. And after that course, I really knew that I liked math more applied on the physics side of things. So that was kind of what started it. And then enjoyed it at university. I really was going to be an engineer. Originally I had a job lined up with Motorola, a semiconductor company. But after my undergraduate degree, liked physics so much, I decided to stay on and go to graduate school and do research. Loved that. Decided to do research as a postdoctoral researcher. So kind of it was a mixture of things, but really that high school teacher was the first one.
I think a lot of us have that one teacher that sort of push our path in a particular direction. We owe them a debt. What initially sparked your interest in collaborating with Auburn Online?
So it was originally a breeding grant that the Biggest Centre gave out. So we had a problem that in the introductory physics courses, the algebra-based ones, so General Physics 1 in particular, that we noticed that some students were struggling with some of the background math that you need for it, geometry, some algebra, a few other things. And It's partly that they might not have done it in a while and be a little bit rusty on it. So we wanted to make kind of a bridge course that brought them back up to speed. So we applied, so we saw the breeding grant opportunity, and we thought we'd apply to make an online course, kind of a math bridge sort of remediation course that the students could do at the very beginning of the course while the course was going on, because it's very fast paced, those courses. So we got the grant, and then the Big U Centre put us together with two people from the math department, and also with Shonda Bowers from Auburn Online, and then the Big U Centre helped us design it. So I think that was the first where I had heard about Auburn Online and online courses and the technology side of things for online courses. So none of us had really made an online course before, and so it was quite an interesting process hearing about how you would design it, what's the best way to communicate it. The thing I didn't appreciate was you have to make sure that the things you're teaching, the things that students are going to do, that you try to measure that, and so it has to be designed in a way that you're covering the stuff that you want them to know, and that you have ways to check that they did learn it during it.
Right. So you're working on a project now related to the MCAT and helping people taking the MCAT score better on the physics portion of that. Could you talk about that project?
Yeah, that's been one of my favorite things to do. And so the pre-health students who are going to become doctors do an exam called the MCAT, and it's 4 exams, very difficult exams really. One of those exams has a physics part to it, about 20 to 30% is physics questions. And the physics they're asked about is stuff they've already done in our physics classes here at Auburn, or any Physics 1, Physics 2 class. But the MCAT style of questions is quite different from the way you see it in physics. So there'll be like a passage that you have to read, first of all, lots of redundant information, and then some multiple choice questions on it. So the idea for the MCAT course is to take advantage of the fact that the students have already seen the material and probably did quite well in the physics courses. They mostly need help to translate the stuff they know from physics into the kind of questions and the style of it that they see. This has been an interest of mine for quite a while, and myself and another physics faculty member, Marlon Simon, about 10 years ago, we used to do evening study classes for the students, just kind of drop in, we could help them with the physics part. Our feeling at the time was that the students are taking our physics courses, or at least that subset of students, so that they know the physics material for the MCAT. So it'd be great if we could help them just make that extra step and take advantage of what they know already from the class and not be so scared by the physics part of it.
How does this project approach the content differently than a traditional review course? You said you did the in-person review courses for a long time.
Yeah, that was interesting. When we talked to the Big U Centre folks about it, it was quite different, because here we're really not trying to teach the material again. So what we decided was that we would take the different topics and on each one give a very short review, really not teaching it again, just a reminder of the equations, what things mean, and then a couple of examples of it. Enough that it just kind of triggers their memory about what they already know. And then the bulk of it is really them practicing the questions, in particular the MCAT style of questions where it's a passage. They never get to see that style in a physics course. So the idea is we have a very short review where I do some learning glass videos to kind of remind them of how to think about it. And then they have some very short physics kind of style short questions so they can practice the skill that they need. And then a bigger test bank of MCAT questions on just physics that they can then use. And also the other thing that's different is that it could be that these students are already pretty good at a good chunk of the course, in which case they should be able to just jump into the bit that they struggle with. And so the modules were designed that someone could jump in and just do the energy section and not do the other parts.
Right.
And the other thing that was kind of different once we thought about it was there's a bunch of kind of soft skills in this where you have to know how to read a graph quickly. And it's not that they don't know how to do it, but there's kind of efficient ways to get information from graphs, or math shortcuts because they don't have a calculator. So things that they wouldn't really need to worry about in physics, but kind of if there's some math skills they can practice.
So you have another project on spectral diagnostics.
Right.
What exactly are spectral diagnostics, and how did you make them engaging in the digital format?
So that course was really much more like my research. So spectroscopy is when you take the light that comes off of a hot gas or a plasma that's really either a research plasma on Earth or an astrophysical plasma in space. And it's the how do you interpret the light from that to tell you, does that have carbon or oxygen, or what's the temperature, what's the density? And so it's really designed, it's a course that I taught in person as a regular course at Auburn on spectral diagnostics. And then the idea was to make it into an online course that would be available a bit wider. The real origin of it was there was an NSF EPSCoR grant that Dr. Ed Thomas got in physics. He's now the dean, of course. And part of that grant proposal was to make some online course material. And that grant was designed to train plasma researchers across the whole state, and from Huntsville to South Alabama to Auburn and a bunch of other places. And so we did recorded videos kind of like this at the beginning of each module. I found them super embarrassing to do, but actually it did help a lot. That way the student doesn't just see the physics material, but they have a face and a voice to put behind it. And then we did a bunch of learning glass videos. And so I think of those in that course as like worked examples I would do in a class on the board. They got translated to learning glass videos where I can talk through it. And then the thing I learned the most was that for a course like that, where it's quite specialised, you want as many ways as possible of the students getting the information. So that went from a learning glass video to some text with equations to another video they would watch. Or Biggie also paid someone to write some computer codes to do little simulations and little kind of tools that they could play with. And then once all of that was done, then you had to assess it with some questions and get some feedback on it. And so basically we took what would have been a lecture course and translated each part that worked in a lecture course into the equivalent in an online one, either the learning glass videos or in-person videos or little kind of codes they could play around with.
Did you see any shifts in student confidence or student performance as a result of these changes? Yeah,
I think so. That was the first real kind of there's not that many online spectroscopy courses. I don't know that there's any other ones. There are books and courses at universities on it. It was the kind of thing that probably a lot of students wouldn't have the chance to do it unless there's someone at their university who does exactly that research. So it kind of opened up things to a broader range of students. So since we developed the course, I've given it a few times to University of Tennessee, Knoxville students who wanted to do it for the research. It was a chance for me. So I give it two different ways, either online where they just go through the online material, or I give it where I give some lectures and it's supplemented with the online material. And all the students doing it are really because they want to do research using it. So they're quite motivated already to kind of use it. And so by the end of it, they seem to me pretty good at actually using it. And we show them some computer codes during it that they can use in their research. So that course has probably led to more research collaborations than anything. That for my own research, where we keep the connection with the student afterwards, they're usually graduate students, and they keep talking to us, we collaborate, and afterwards they come and visit us, things like that.
So looking to the future, how do you see technology reshaping physics education over, say, the next decade?
Yeah, that's
tough to.
Yeah, that's right.
They say it's tough to make predictions, especially about the future.
Now. Yeah, so I think that because the thing everyone's talking about is AI. I think my own take on this is that if used properly by the students, AI's technology could really be a great kind of extra tutor or help for them. That originally the AIs were not very good at physics. They weren't very good at numbers. They're getting better quite quickly. I think in a course, if I was a student doing a course and I had a particular thing I was struggling with, in many cases asking an AI to explain it to you, I think is a very good explanation, or asking it to make up a question that tests that you can then do. It's maybe at the stage just now where it's going to make mistakes and still, but probably that'll get better quite quickly. And I think that it's you could use it to supplement the help that you get from the instructor, where you deal with certain questions with you and an AI talking back and forth with each other, and then take the questions you're really stuck with to the person teaching the class and iterate on that. So I think that it has the potential to really make the education quite tailored for each student. But I think if the courses are designed so that AIs can be used in the right way by the students, and we still test that they can do it on their own under test conditions, then I think that the students really could come out with a direct kind of addressment on their main misconceptions and cleared up.
What do you think is the biggest myth the typical person would have about physics?
Oh yeah. I think that no one's going to believe this, but I think it's that physics is hard is the myth.
I definitely believe that.
Yeah, I think that's a common thing that people think. Us on the physics side, we don't think of it that way, and it really isn't. It really isn't that hard. It's either seen as being hard because it's quite mathematical. But in physics, there's really just a small number of things you have to know, and then from that you have to figure out what to do with it. There's a small number of equations, and then you have to use that in a wide range of scenarios. So I think if physics is learned in a way where you're not trying to memorize all the ways that things can be asked on a particular topic, but you're memorizing the one equation you need for that scenario, then you can apply it to a dozen different ones, then all of a sudden physics becomes simpler. And that was what was the breakthrough in my thinking in high school from that teacher, that we were doing rotational motion, and all of a sudden I realized the same equation described airplanes banking around a curve, cars going around and a kind of banked plane, motorcycles leaning into the curve, things going around on a string. It was all the same equation that described it. And then I realized that these things that I thought of as being very different physics scenarios were all the same physics scenario. And it became a kind of shorter way to suddenly understand all those processes. So, and I think the students who come through, hopefully enjoying physics at the end, is often, I think, because of that, they thought it was going to be hard, and it wasn't as hard when they came to their side. At least, hopefully, that's what they think.
So it's probably Einstein's fault that everybody thinks physics is
that's right.
difficult because he was so amazingly intelligent.
Yeah, that's right.
What's the best advice you ever received as an educator?
So yeah, I interestingly, I don't think that I don't remember people giving me advice so much that, but I think that. So I don't know who told me this, but I think the best lesson that I learned, which must have come from someone, was to find the method in the class that suits your personality the best, and rather than trying to lecture like someone else that you like their lecturing style, rather than trying to pretend to be them or borrow on their method because it worked well for them, the best thing is to find ways of teaching that are natural with your personality. And so I think that, and that means it's different from everyone,
right?
But it means that for me in Scotland, a common way to communicate is to tell stories, and we're kind of storytellers by nature. And so I discovered just by accident, and though maybe by people talking to me about it, that if I can make the lecture into a story where it has a narrative with a beginning and a middle and end, and I have points along the way, then that provides a framework for how the lecture works, and it keeps the students engaged because human beings naturally follow stories and like stories. And anything I could do that kind of, otherwise you're trying to do things that don't really fit with your personality, and it seems kind of fake. And so when I give people advice, it's more like that, is to find the things that work. Be yourself, yeah, right. And then what's really needed is to find ways of being yourself that work in the class, rather than just be yourself completely. But to take the bits of teaching where you being yourself can use a certain already established teaching method of the way you do examples on the board, or sometimes that you like discussions in the class, and you can actually manage those discussions pretty well. So kind of take advantage of the way that you think already.
So last question, what is your go-to local restaurant when you have guests from out of town?
So often my guests are coming from outside the country, and often from Scotland or Ireland or England. And so I like to take them to Acre, partly because it's southern. They get to see southern foods and really good food in a nice atmosphere. And it gives them a kind of a taste of southern cuisine and hospitality in a nice environment.
Yeah. There. Good answer.
Cool. Thanks.
Well, Stuart, this has been really fascinating, and I could probably talk about physics for hours. But
me too.
We appreciate you being here, and we appreciate all the exciting projects you're working on in the online environment to make students' learning experiences better.
Thank you. I appreciate you asking me to come here. It's been a lot of fun.
Excellent. Please join us next time for our next fun-filled episode of TigerBytes.
Thank you for joining us for this episode of TigerBytes. We hope you enjoyed the conversation and gained some valuable insights. Please like, subscribe, and share this podcast with your friends and colleagues. You can find us on all major platforms. And keep learning, keep growing, and we'll see you next time on Tiger Bytes.